So let's say lecture 12 today, right? And we're going to say more on boundary layer theory. And let me see whether I actually told you which chapter or the section number it corresponds in the textbook. Yeah, I told you which chapters we are dealing with, right? Okay, good. Again, chapter 19.4, 19.6. Let me write it down. Still chapter 19.4 and 19.6 we're dealing with. Let me go back to where we left. Let me talk a little more about what we have done so far. We actually talked about the thermal boundary layer. We denoted the boundary layer thickness delta T, and we say that it has similarities with the hydrodynamic boundary layer. At least the equations came out to be pretty much similar. We said that it's alpha, if it's replaced by nu, we get this exactly the same condition. So we said, why don't we just solve this equation for the case alpha is equal to mu, which corresponds to Prandtl number 1. And for that particular case, we came out with exactly the same governing equation, with exactly the same boundary conditions, but with a small detail there. The boundary conditions we needed to non-dimensionalize to make them exactly the same for like in the hydrodynamic boundary layer case. And then we got the same equation. We said that the temperature profile is exactly the same as the velocity profile. Okay. And we said there are actually more similarities, like, for example, the shear stress near the surface is identical up to a factor of multiplication to the heat transfer at the wall, the heat transfer rate or the flux at the wall. So we related to the two, and we wrote the shear stress at the wall in terms of the skin friction coefficient, and we came up with this beautiful non-dimensional formula, which tells us that the half of the skin friction coefficient is equal to a dimensionless number, which is called as the Stanton number, that we called as the Reynolds analogy. And but we should say we said that we should keep in mind that we made this equation correct in the assumption of Prandtl number is almost 1. Okay. So that was what we learned yesterday. Okay. And let's do more on this. Let's elaborate more on this, and let's talk about other cases. You can ask the question, what if the Prandtl number is not equal to 1, right? That's a legitimate question. And we can come up with another case. We can call it case 2, right? Case 2. Let's imagine that the Prandtl number is not equal to 1. Specifically, let's clarify it. Let's make it much, much less than 1. And then maybe we can have a case 3 in which the Prandtl number is much, much larger than 1. So we can actually investigate all 3 cases, all possibilities, right? This means the following. The kinematic viscosity divided by alpha is much, much less than 1. And that corresponds to, since we know that nu over alpha, the Prandtl number has something to do with the delta over delta T, the ratio of the boundary layer thicknesses, then that must also be much, much less than 1, right? We actually argued that if I have a larger nu, I should have a larger delta. Similarly, if I have a larger alpha, I should have a larger delta T, right? remember that argument. So if nu over alpha is much, much less than 1, one would expect that delta over delta t would be much, much less than 1. The reason is the following. So like you can ask the following question, oh, that's nonsense, because I mean, maybe the delta originally was already much, much larger than delta t in reference, but one can argue that your reference case could be like Prandtl number 1, and you know exactly that at Prandtl number 1, delta is exactly equal to delta t, right? Because you have exactly the same governing equations, same boundary conditions, so one would expect delta would be equal to delta t for the case of Prandtl number 1. So if one increase delta more and more and more, or maybe if we increase, so if we decrease the nu more and more and more, we're going to get a smaller and smaller Prandtl number, and that would keep the delta t the same, but the delta would get smaller and smaller, right? That's what one would expect. So it's not a it's I think it's reasonable to argue that delta over delta t is also much, much less than 1, right? And then let's have a picture of the situation. Now, so this is your thermal boundary layer. Your delta is going to be very small. So let's say you have this, okay? And the delta is this much. This is your delta, which is the hydrodynamic boundary layer thickness. And then you have this thing for the temperature. Let's imagine that the delta t is much, much larger. So you imagine that your delta t is this much. So it's exactly the case where the Prandtl number is much, much less than 1, right? And you can call this T infinity. You can call this T wall. And this can be your, this can be the temperature, right? The size of those lines. So that's what we are investigating right now. Let's rewrite the thermal boundary layer equation. Thermal boundary layer equation. As you remember, Vx del T over del X plus Vy del T over del Y. Let me clarify, I don't expect anybody to memorize this, because you have your notes and textbook and you know where to find the information. So it's not memorizing the equation, but it's all about whatever you're going to do with the equations, right? Alpha del squared T over del Y squared. Now let's do a order of magnitude estimation, like some sort of scaling analysis, right? So you can argue that this first term scales with V infinity times delta t over L, right? Because the characteristic length for the x is L. We're talking about the changes of temperature of delta t, such as T minus T infinity or T wall minus T infinity, and Vx is in the order of V infinity. The second term, on the other hand, is going to be in the order of V delta T delta T or delta T. Okay. So so basically, you know that the Vy divided by delta T is in the same order of magnitude with the V infinity over L, so you can replace it by V infinity delta T over L. So they are actually in the same order of magnitude. The term on the right-hand side scales with alpha delta T over delta t squared. Okay. Right, any questions so far? I mean, this one we get from continuity equation, right? Because it gives us a rough relation about the Vy and Vx, so you replace the Vy with Vx roughly. Okay. That's the thermal boundary layer equation. Continuity equation, let's write it down just for your reference. Del Vx over del x plus del Vy over del y is equal to 0. We said that this is in the order of V infinity divided by L, and this is in the order of V delta t over delta t. So you can actually claim that these two are in the same order of magnitude. Okay. Now let's have a look at this. Now, what is my region of interest? Here. My region of interest, I want to solve the thermal boundary layer equation. So my region of interest is the thermal boundary layer, this one, not this one. So I should not focus myself to delta, but the delta t. Oops, let's write it down here. Region of interest is the thermal boundary layer. So from thermal boundary layer equation, what do we get? We get the following. Have a look at this expression. This must be in the order of this, right? Because you have an equation, the left-hand side must be roughly, one must be equal to each other. So in other words, they are roughly equal to each other, right? And this is the advection term, and this is the conduction term, right? So your thermal boundary layer equation tells you that advection is approximately conduction, right? In other words, the infinity delta t over L is in the order of alpha delta t over delta t squared, right? And you can actually get a sense of the delta t over L. So let's actually get the delta t over L. Since I have the delta t squared there, let me square both of them. So delta t squared over delta t squared over L should be in the same order of magnitude as alpha delta t's cancel, right? Divided by V infinity. But you have one more L because I want to make this L squared instead of L. Okay. So this is nothing but 1 over, which is the -1 power of the V infinity L over alpha. Okay. Yeah. Does it look like something? Does it look like a dimensionless number that you already know? Well, it's not the Reynolds number, but it looks like the Reynolds number, right? But I need to change the alpha to mu to make it Reynolds number, right? So let's actually play with it a little bit. So we can say V infinity L over alpha um, is equal to V infinity L over, let me divide by nu and multiply by nu to make nu, to have nu in the denominator. We have alpha. And now both of the numbers are actually familiar, right? This and this. So this is nothing but the Reynolds number, L, and the Prandtl number. Okay, now we have a new dimensionless number. We should celebrate it, right? Anytime you actually come up with a dimensionless number that's new and that nobody else knows, you should celebrate it because it's probably something very important. This one, this is called Peclet number. Okay. So probably you're getting a little frustrated because the number of dimensionless numbers is getting like more and more each class. But the good news is you have the textbook and you have your notes. As long as you use those things, you're gonna get used to them and you're gonna learn them better. And when you solve more problems, they're gonna be part of your knowledge, and you're gonna know them by heart. Okay, so what does this mean? So what is this Peclet number? So I get something like 1 over Peclet number here, but what is it? I mean, the reason I'm investigating it because it's probably something very important, right? Because it tells me an idea about how large is the thermal boundary layer, right? So let's make sense of it then. So let's see, Peclet number is equal to, we said it's V infinity L over alpha, right? Instead of alpha, you can write down K over rho Cp, correct? So I replaced the alpha by K over rho Cp, the definition of the thermal diffusivity. That's equal to V infinity. Let's what are we gonna do here? We're gonna multiply by delta t both sides, and I'm gonna take the L to the denominator. Okay, so I'm gonna have V infinity rho Cp. Let's multiply both sides by delta t, or both numerator and denominator, and divide by L, the K by L. Okay, so I got this L to here, which I can, because 1 over something is that something. It's equal to, as you can see, the numerator is something similar, something actually familiar, right? It's the advective heat flux. It's the heat flux caused by the motion of the object itself. It's like you're moving your hot coffee from one place on the table to another place. It's just because you're moving the object, the heat is being transferred. So that's the advective heat flux. Right? Divided by the K over L delta T is something familiar as well. That's the conductive heat flux. Okay. So it means the following, actually. It looks like the following thing. So imagine there is like a hot object, not as hot as it's gonna burn your finger, right? You're touching this part of the object, or maybe, yeah, let's touch this part of the object. Okay, and then this is hotter, and this is colder. Okay, and imagine your temperature profile is something like this, right? And if I actually push this object to the right, and if you just don't move your finger, then you're gonna feel, as time goes, you're gonna feel like this part of the object instead. But meanwhile, the conduction also is taking place. So it's a matter of which one is going faster. Am I moving this object faster? Is the heat being transferred mostly just because I'm moving this object faster? That's the advective heat flux. Or is it because the material is so conductive that I can just feel the conduction? So if I just don't move this object, the conductive heat flux is going to dominate, meaning that your Peclet number is going to be very small. But if I start to move this object really fast, not allowing the conduction to happen in a short time, then your advective heat flux will be large. So then you're going to get a large Peclet number, right? So that's the essence of the Peclet number. And in this case, the object that I'm actually giving an example was a metal bar, but normally we are talking about fluids, but doesn't matter. It's just because the fluid is moving, the energy being transported. Okay, it's the same example. Okay, so what does it tell us? It tells us the following. So let's put a reminder here. Recall delta over L was in the same order of magnitude as Reynolds number L to the power -1/2, right? We did the scaling analysis, and we also have like a particular solution for that, and we know the proportionality constant between them for approximation up to third order polynomial. So this is from the derivation for hydrodynamic boundary layer. Correct? Okay. Now, there was another thing, right? Oops. Said that delta over delta T is scaling with the Prandtl number to the power 1/2, right? We said that delta over delta T qualitatively depends on the ratio nu over alpha, right? We wrote down these things before. Okay. Let's now derive the expression for the Nusselt number. Now, what is the reason that we are deriving an expression for Nusselt number? Do you know the reason? Why am I actually caring about the Nusselt number? In these maybe 3 or 4 classes. What have you done? Yeah.
To derive dimensionless numbers.
But what is the purpose? So let's go back to our original intro to boundary layer. So maybe the title boundary layer is a misnomer for this, but I should have used convective heat transfer. So what am I trying to find? What is my very first objective that I set down and I sometimes seem to forget it? What is that?
Is it the value of H?
Exactly, the value of H, right? We said, so far we said the Newton's law of cooling says Qs is equal to H times Ts minus Tf. But we said, let us learn how H can be estimated, right? We want to estimate the H. And the most direct way to estimate H by knowing the Nusselt number, okay? And it's always the case. If you know the flow conditions, you first try to calculate the Nusselt number. And then, since Nusselt number gives you an expression relating the H to the conductivity of the material, K, then you can solve for the H by knowing the Nusselt number. So that's the reason why we are actually obsessed about the Nusselt number, okay? So we want to desperately know what the Nusselt number is for a problem. Okay. Now, so here's the thing. Let's write down the following now. Okay, so I'm going to write down an equation, which is the conductivity. So let's say whatever is transferred or let's say the following. The amount of convective heat transfer should be regarded as the conduction taking place at the very boundary or let's say at the very surface or interface separating the solid and the fluid. Okay, I mean the following. I have this thing. Imagine that there's a very infinitesimal layer. Oops. Yeah, there's a very small infinitesimal layer of fluid here. I'm not talking about the delta, the boundary layer thickness. I'm talking about a much, much smaller region, maybe like 1 atom size region, right? Infinitesimal interface. Okay, now the heat is being transferred here, conducted, is whatever is being lost by the solid, right? So you can actually say that that's the heat flux that I would like to calculate, right? That's the H that it relates to. So you can say that from the Fourier's law, minus K of the fluid, let's work on the fluid side, del T over del Y at the wall, near the wall, is equal to whatever is lost by the solid, which is basically Newton's law of cooling, right? H times T wall minus T infinity. Although T infinity is here, T wall is here. This is just like approximation. So if you know T wall and T infinity, the question is what is the Q? Okay, so you can write down this equation, but this term on the left-hand side relates to whatever is happening here in this region. Okay, and we claim that whatever is conducted at that very tiny, thin, infinitesimal interface is the amount of heat which is being actually lost. Okay, let's work with dimensionless numbers now to simplify this equation. Now, theta is equal to T minus T wall divided by T infinity minus T wall, same as we did before. Okay, just give me a second. Okay, and dimensionless y, let's call it y tilde, is equal to y over L, length of the object. And then if you do the replacements, if you replace T by theta times T minus T wall plus T wall, you get minus Kf T infinity minus T wall del theta over instead of del y, you can say del y tilde over L, right? Y is equal to L times y tilde, that's fine. And at the wall, the y tilde is equal to 0. That's equal to h times t wall minus t infinity, right? And this thing times minus is actually exactly the same as this thing. So you can say, let's cancel them. Right? And you come up with the following. So for del theta over del y tilde is equal to HL over KF. F just reminds us that it's the fluid conductivity. And what is this number?
The Nusselt number.
The Nusselt number, excellent. And we put L just to denote that we are using the L to calculate the Nusselt. We are using L as the characteristic length, okay? You can use X like at any distance X, so that's called Nusselt number X, like we defined the Reynolds number X versus Reynolds number L. Okay, so what does this say? This is a remarkable formula, right? Look at this number and look at this thing. So what does it tell us about the Nusselt number? This means that the Nusselt number is nothing but the temperature, gradient, right? Because this is a temperature gradient, but in non-dimensional form. Gradient at the wall in dimensionless form. So we got a deeper and much better physical insight about the Nusselt number, right? So we are actually growing our intuition more and more about the Nusselt number and about what it means. Okay. Also, you can do some sort of scaling analysis again. Minus kf del t over del y, y is equal to 0, is equal to h, t wall minus t infinity. And you can say this is in the order of kf times delta t divided by delta t, right? Because we are particularly interested in the thermal boundary layer, not the hydrodynamic boundary layer, and they have different scales. One is maybe like 100 times larger than the other. And this one is in the order of h times delta t. And from this, we find the following. Kf delta t over delta t, the one on the left-hand side, scales with h times delta t. And the delta t's cancel. What do we get? H delta t over kf is in the order of 1. Okay. And so that's another thing. Let's put it aside. Now let's have a look at the Nusselt number estimated at x instead of L. So this is Nusselt number at x is equal to, instead of HL over K, we have HX over KF, right? That's equal to H. Let's multiply and divide by delta T to make it actually look like this thing, because I want to just make use of this thing. So I did not do it for no reasons. So delta T over KF times X over delta T, right? And we know that this is in the order of 1. Okay, but the entire thing must be in the order of, so here let's actually do it this way. Now have a look at these two things. Okay, so okay, from here one can get the following using the 2. Divide the one on the top, divide the one on the bottom by the one on the top. So basically delta over delta T divided by delta over L is gonna scale with Prandtl number to the power 1/2 and Reynolds number to the power 1/2, right? And after canceling the deltas, you find the following: L over delta T is, by the way, this is Reynolds number L, Prandtl 1/2, Reynolds number L to the 1/2. Similarly, you can have X replaced by L, L replaced by X. Delta T is approximately Prandtl number 1/2, Reynolds number X 1/2. You know the definition of Reynolds number X, so you can use that one. So have a look at this. Okay. Now you know that it's in the order of, that X over delta T is in the order of Prandtl number to the 1/2, Reynolds number X to the 1/2. Okay, good. Okay, good. So this entire thing is going to be Prandtl number 1/2, Reynolds number X 1/2. Okay, good. So the Nusselt number, although we haven't probably derived this one before, I think this is the point where we should state this. So Nusselt number at X is scaling with the Prandtl number 1/2, Reynolds number X 1/2. Okay. So that's an excellent equation. That's valid for any case, right? So we, yeah. Okay. Okay. Where did we use the delta is much less than delta T assumption? Okay. It looks like we have not used that, right? Okay.
No, wasn't this whole class delta was less than delta T? Because delta over delta T is less than 1. So
Yeah,
I'm assuming
where did you use it?
on the top of the top.
Here?
It says delta over delta T is much less than 1. So I'm assuming delta is less than delta T.
Yeah, did we make use of it? That's what I'm asking.
I don't think so, no.
Okay. So could this be valid for any case? What do you think?
I think so, yeah.
Yeah, this could be valid for any case, correct?
Correct, yes.
Okay. So let's think about the case 3. Maybe we can actually learn something else from this case 3. Prandtl number is much larger than 1. Okay, meaning that delta is much larger than delta t. Let's see whether this is going to give us some different insight or some more further simplifications. So imagine that this is your hydrodynamic boundary layer thickness, delta. This is V infinity. Right? And this is T wall, right? And this tiny thing is delta T, correct? Now, just a second. Let's go back. Okay. Have a look at this order of magnitude estimation. We say that the Vx is scaling with V infinity, right? Although this is valid for Prandtl number almost equal to 1 and much less than 1, this is not valid for Prandtl number is much larger than 1. The reason is because you can see that at any point here, at any point, most of the regions, my V is almost equal to V infinity. So I can do that assumption. So in my scaling analysis, this is not possible for Prandtl numbers much larger than 1. Okay, so that's an important thing to mention. Is that clear? Now this is definitely, so this analysis is valid only for Prandtl numbers much less than 1, but not much larger than 1. Okay, is that clear? So that's why we have another case here, and this is T infinity